Section 3.3, we're going to look at what's called the empirical rule and measures of relative standing. So this is going to allow us to identify the range of values associated with a percentage of our data, as well as finding ways to describe where a data value lies within a distribution. So the first thing that we need to talk about, though, is how can we describe where most of the data is located? Whether that most is 50%, 80%, 99%, where could we find some percentage of our data? So we'll start with Chebyshev, and this rule is going to apply to any distribution. So this is powerful because we can do this whether the distribution is normal or not. Anytime that you have some number of standard deviations more than one. Okay, so you want K to be at least 2, to be at least something greater than 1, 1.1, 1.2. But if you have some number bigger than 1 of standard deviations, we can describe what proportion of our observations are going to lie within that number of standard deviations of the mean. So if I go 1.5 standard deviations from the mean, what proportion of my observations will be in that interval? And we get that formula by doing 1 minus 1 divided by our k squared. This graphic helps you see what we're talking about. You have your mean, and if we go out some number of standard deviations greater than 1, it can be 1.1, 1.5, 2, 3, whatever. But if we go that number of standard deviations on both sides, then we're going to capture at least 1 minus 1 over k squared of the observations. Example 3.11, we're looking at a random sample of the Optima red top automobile battery and looking at the lifetime in months. So here we get a sample mean of 54 months with a standard deviation of 5.3 months. And we want to use Chebyshev's rule with k equals 2 and k equals 3 to determine what percentage of observations will lie in a particular interval. So for k equals 2, we'll do 1 minus 1 over 2 squared, which 2 squared is 4, so we're looking at 1 minus 1/4, 0.75 or 75%. So we can say that 75, or at least 75% of observations will fall between 2, since our k is 2 standard deviations of the mean. We also want to give this interval. So let's take our x bar and subtract 2 standard deviations. So we take our 54 minus 2 times that 5.3, and that gives us 43.4. So that 43.4 represents, if you take the mean and you subtract 2 standard deviations, if we take the mean and we add 2 standard deviations, so that's 54 plus 2 times 5.3, that's going to take us up to 64.6. We now can say that 75%, or at least, I keep forgetting that, at least 75% of lifetimes of these batteries will fall between this interval 43.4 and 64.6. So if you're trying to decide if you should buy this battery, if you're comfortable with being between 43.4 and 64.6 months, then this would be the battery that you should buy. But you'll see that several of the batteries will die before 4 years, and so maybe you don't want to purchase this battery. So this just gives us an idea of what percentage are falling kind of in this middle range. If we go to k equals 3, then here, 1 minus 1 over 3 squared, or 1 minus 1/9, you end up with 89%. So at least 89% of batteries have lifetimes between, and this time we'll take our mean and we'll subtract 3 standard deviations and add 3 standard deviations. So we have 54 minus 3 times 5.3, which is 38.1, and 54 plus 3 times 5.3, and that gives us 69.9. So now 89% of our batteries we know will last between 38 and 69.9 months. This kind of information is useful because if you are going to buy a product, you want to know that it's at least going to last a certain amount of time. We talk about having a guarantee on products. And so if the manufacturer were to offer a guarantee, then a good cutoff value here might be 36 months. Because 89% of your batteries are going to last between 38 and 69.7 months. And so it would be relatively unlikely for something to last less than 36 months. And so here you can guarantee against some of the more defective batteries, but be ensured that most of the batteries are going to last in that 38 to 69.9 range. So that's why we would do something like this. Now, if we look at example 3.12, we look at a different way of applying Chebyshev. And so here, this is looking at the random sample of songs produced by classic rock bands to look at the time of them. So the average length of these songs was 3.35 minutes with a standard deviation of 0.5. And so if we wanted to know the approximate proportion of observations between 2.35 and 4.35 minutes, we need to know how many standard deviations this is. So we start with the mean, 3.35, and if we subtract 1 standard deviation, that takes us to 2.85, but that's not where we're going. If we subtract 2 standard deviations, that takes us to 2.35. So here we are looking at going 2 standard deviations. Here, so if we do our 2 standard deviations, Chebyshev tells us that 1 over 2 squared, or 1 minus 1/4, or 75% of observations will be between 2 standard deviations, which tells us that 75% will be within 2.35 and 4.35. For part B, it's asking for observations less than 1.85 or greater than 4.85. So this time we can still figure out how many standard deviations. This is going 3 standard deviations. If you subtract the standard deviation 3 times, you get to 1.85, and add, you get to 4.85. But Chebyshev, what it's saying is that 1 minus 3 squared, or 89%, will lie between. But that's not what this question is asking. This is things that are lower than 1.5 and above 4.85. So if we've got some distribution, we're looking for the things below and above these numbers. We found that 89% is within, so we want to find what's beyond. Subtract that from 100, and you get that 11% will be beyond. So just be careful on what the question is asking, because in this case, we wanted to know what was beyond, not what was between. And then sometimes we'll have questions that are not an exact number of standard deviations away. And so we need to have a method that allows us to figure out what happens when we can't calculate the number of standard deviations just by adding and subtracting multiples. So here's a question, approximately what proportion lasts more than 5 minutes? Well, 5 minutes, I can't get to that simply by adding and subtracting 0.5. So take your sample mean, which in this case is 3.35, and then add, for this case, you can add or subtract, but this is a higher bound. So we will add here our standard deviation, and we want to get that to equal 5. So we have to do just a little algebra here. We need to solve this equation for k. So remember, we can start by subtracting 3.35, and I'm going to rewrite this as 0.5k. We subtract, we do 5 minus 3.35, we get 1.65. Divide by 0.5, divide by 0.5, and that gives us that k is 3.3 standard deviations. We can still use Chebyshev for these non-integer values. It's still 1 minus 1 over k squared. So 1 minus 1 over 3.3 squared. And you get 91%. But let's think about what Chebyshev is actually saying. 91% will be within 3.3 standard deviations. So if we take our 3.35 and we subtract 3.3 standard deviations, that takes us to 1.7 minutes. And then we already figured out that 3.35 plus 3.3 is going to get us to this 5 minutes. But I'm not interested in between. I'm interested in exceeding 5 minutes. I just want this stuff. But what I know is that 91% will be here. So, we don't know if these are evenly spread. We really have no idea. There may be nothing in that little tail, or there may be, 9%. All we know is that 9% is going to be within 1.7 and 5 minutes. And so all we can say is at most 9%, just the leftover. It may be 9, it may be 5, it may be 8, it may be 2. Anything below 9 could be up in that tail. So for these distributions, we do have some limitations because we don't know that these two sides are going to be symmetric. So in the next video, we'll look at what happens when you know that you have symmetric data, because you'll be able to say exactly what percent instead of saying at most and at least.